Good afternoon, all. We are here for the last session today. In this hall will be on hydraulic design, and I'm doing that with I'm Adriaan and I'm doing that with Bruce Ashcroft and Joachim Perez. The three of us will try to finish in time. So in the second generation of Eurocode, there's a lot of focus on groundwater, and that is because groundwater is something which is a force which is often under-evaluated, but the effects can be disastrous. So we have in part 1, clause 6, on groundwater levels and groundwater pressures. There is a chapter in clause 8 on limit states in groundwater, so uplift and hydro flow. There is in part 2 a clause on how to derive your geohydraulic parameters, and there is in part 3 a special clause on groundwater control measures. And I will go briefly through them. First of all, measurement of groundwater levels, normally done in a standpipe by doing a hand reading, or automatically when you lower a so-called diver, a remote reading device, or by putting in a piezo cone or whatever. And then some definitions on groundwater. The groundwater level is the level of a water surface in the ground, which is seems very clear. But piezometric level is the level of a pipe and water in a standpipe, and there you have, of course, the difference between pressure water and free water. And the groundwater pressure U is related to the groundwater level which you measure. So Z is the elevation, and your HW is then your piezometric level. So you can convert easily between levels and pressures. Then having those measurements, how do we get then representative values of groundwater pressures? Because that's what we really are interested in. There's two ways to do it. It's in section 6.4. You can do in the left, the top line. Yeah, your top line, you see that you can take or the upper one and the lowest one as or the lowest one as your representative value, or you schematize it as an average value, GW, with an amplitude Q representative. And then those values of G are based on probabilities, and probability of exceedance of 2%, which is roughly speaking a 50 years return period. And it's referred to a clause in EN 1990. And that's the way you do it. That's the definition. And if you have lots of groundwater measurement data, you use this procedure. If you don't have much data, then you have to choose it, and then we call it nominal values, and those are the cautious estimates. And when we look at the representative values of the amplitude, we can, according also EN 1990, we can distinguish a characteristic value, which has just like the permanent one in the previous slide, a 2% probability of exceedance. A combination value, that is in case the water is not a leading component, and it has a 5 to 10% probability of exceedance. A frequent value, which is a value occurring in 1% of the reference period, and a mean. And of course there's also an accidental one, which is corresponding to a 0.1% probability exceedance, so there's a 1 in 1,000. How does it work? I got this from a colleague from Deltares. If you have a certain groundwater level reading, it looks like this, and here in the vertical axis you see it in centimeters. And what could you do? You can analyze an extreme value. You look at all those extreme values, and you can make a kind of distribution, how often they occur during your lifetime, and you get typical graphs like this. These are the various points and the frequency of occurrence. These are of course very frequent, and these are less frequent. And you can even extrapolate when you want a 1 in 50 years value. That would be a way to deal with these values. But you need, as said, a great amount of data. Well, for the frequent value, it's a bit different. It is exceeded during 1% of the period. So then you should make a kind of histogram and a curve like this, and you look at a 1% value of occurring. Now these are the numbers, but I think it's not so important. I must say there's recently there was a paper in the EC7, the conference in Lisbon, from Timo Schweckendiek and José Estaire and Andrew Bond on this procedure. And then we go to design values. So how do you have your problem, you have a representative value, but how do I get a design value? And according to the code, you can do that in 3 ways. You can do take a direct assessment, for instance, when there is a dike and the water table cannot be higher than the top of the dike or the maximum of the surface. You do a direct assessment. You can also say, well, I apply a deviation. I put a ½ meter on top of the representative value. Or you can apply a partial factor to the groundwater pressure. And if you did the first 2, direct assessment of a deviation, you normally use when you calculate design pressures in effective stress calculations, for instance. But if you have a caisson with a pressure acting on it from one side, you probably would use a partial factor. So both methods are allowed in Eurocode. This is on the Dutch National Annex. I do not want to stand there very long. In Dutch National Annex, as an example, we have 2 methods. One is the statistic one, and the second is where we have the design value is equal to the characteristic one, so the representative one actually, GWK sub, and then a factor between the representative and the average we put on top of it. So it's 1 or 0.5. These kind of estimates are very useful in practice, but sometimes you have to to be very much aware of what you, if it works in your case. And check up uplift. I think Joachim will talk about this in later things. There are two ways of dealing with uplift. One is, for instance, a caisson with tension anchors underneath, and the equation is the representative force, the uplift force, plus another uplift static force, plus a water force due to variation, and a variable uplift force. So these are all uplift forces, and there is a vertical force due to the weight of this caisson acting downward with a partial factor gamma g favorable, and that should be less than the resistance of those anchors should be greater than the sum of all these components. The factors have to be applied according to EN 1990. Here are the numbers. I think Joachim will discuss this further. I just want to say that if you want to change these values in your country, you have to go to EN 1990. We cannot do that in the National Annex of EN 1997. You have to go to the National Annex of EN 1990. The other case on uplift is a fact where you don't have a caisson, but an excavation with where you compare not forces, but you compare actually pressures. You have a vertical pressure of the ground against the uplift pressure of the water. Well, and again, the partial factors. The other hydraulic limit state is hydraulic heave, and that is the case where you have a column of ground. Here is a water pressure which is higher than the water pressure on the top side, so you get a flow of water through the soil upward. And if the gradient gets too high, when the difference gets too high, the effective stress in this column is reduced to zero, and you get a hole and erosion. So you want to prevent that, and you do it by keeping actually the effective stress to 1/3 of the original value. That's the safety which is on it. And here you see the lines, the water pressure in case of no flow, it's vertical. In case of flow, you get a deviation of the difference in water pressure, delta U. And this is the effective stress. So with no flow is the original one, but with flow, the effective stress is reduced. And this is the equation which is next to it. I think Joachim will talk about this in greater detail. Then there's a second check. So there's the hydraulic failure I showed before, and it's much used when you have, for instance, sheet piles. You have connecting water underneath the sheet pile. You also can check the internal erosion and piping by comparing the hydraulic gradient with the critical hydraulic gradient. And that's, yeah, of course, you have to look at the direction, the grain size, the layering, and of course, the ICD is a very important parameter, and you find them in, for instance, the CERIO report, the International Levy Handbook. And then, so this is in part 1. Part 2 of Eurocode 7 is on groundwater and geohydraulic properties. And 11.2 gives you the measurement of groundwater pressure and pressure head, gives a number of things where to think on, and also a number of techniques. And it determines the geohydraulic properties, especially the hydraulic conductivity on lab tests, constant head and falling head, pipes in boreholes, so standpipes in open and closed standpipes, water pressure tests in rock mass, I described pump tests, is a very important parameter, of course. Infiltrometer test is the other way around, you're not pumping but you're infiltrating water. And of course an indication by the CPT when you have a piezo cone and you do a pore water dissipation test. So these things are determined in Eurocode 7 Part 2. The last bit about groundwater is in Part 3. There's a special clause 13 and it is called groundwater control measures. And measures for groundwater control, well, we have 3 classes of groundwater control measures. The first one is to prevent water flow. Second one, reduce water flow. So, and the third is control water flow by dewatering. So to prevent water flow, you create an impermeable barrier. And of course, in the discussion, you get immediately what is impermeable. We added a note that a project-defined low value is considered impermeable. And you can do that by sheet piling, grouting, other types of barriers, freezing, diaphragm walls. I think Bruce, you will attend that in your example. Also reduction groundwater flow. It's also grouting, soil mixing, clay layers use. And the third one, dewatering, is drains and wells and other dewatering systems. These are described and measures and monitoring actions are given. Important is the limit state verification. We have here chosen that actually the groundwater control measures is something which has to do with water heights and groundwater levels on both sides of a barrier or an inflow or whatever, and that is more a serviceability limit state. And we have formulated that in this equation where the ED, which is the groundwater of surface water pressure or the conductivity or the flow rate, should be between a minimum and a maximum. And then you can also give your requirements for those groundwater pressures, hydraulic conductivity and flow. So, summarizing, we had a focus on groundwater. In part 1, we had how we have described how you select the representative groundwater levels and pressures, the design values, and the ultimate limit states, uplift, hydraulic heave, and hydraulic gradient. Part 2 gives you how you can determine those pressures and the hydraulic conductivity, and part 3 gives you the groundwater control measures. And that, I think we all do this because we want to avoid situations like this occurring.